Okay, guys, Mr. Antonucci here, and in this video, I want to talk about solving motion problems. And so we've been talking about antiderivatives. So for an object moving along a line, we have the position, velocity, and acceleration functions, S, V, and A. And this would all be of an object at a time t. So these three quantities are related because the derivative of s, or the derivative of position, is velocity, and then the derivative of velocity is acceleration. And since velocity is the derivative of position, then acceleration can also be thought of as the second derivative. Acceleration can be thought of as the second derivative of velocity. Okay, so those are very important relationships. And now, if the acceleration is known of a function, then the velocity can be figured out by finding the antiderivative of acceleration. Similarly, if you know the velocity function of an object, then the position function can be figured out by getting the antiderivative. Now, in physical problems, the values of velocity, position at time t equals 0 are often given, and they're denoted with like v of 0 equals v naught, or whatever number they tell you, and s of 0 equals s naught, or whatever number they tell you it is. And those are typically referred to as initial conditions. So that's going to be some important terminology for what we're doing with motion problems. So let's take a peek at an example here. We want to find the position function s of t of an object at time t if its acceleration a is a of t equals 8t minus 3, and we have some initial conditions for the velocity and position. So if a of t equals 8t minus 3, then the antiderivative of that would be the velocity function. Remember, we take the exponent on the t is understood to be 1, so the power rule is you add 1 to the exponent and multiply by the reciprocal of the new exponent, which would end up making that 4t squared, minus 3, the antiderivative of 3 would be 3t plus c. So v of t equals 4t minus 3t plus c. This is what we would call the general solution because it has the general antiderivative. We can get the particular solution using the initial condition that v of 0 equals 4. So v of 0 equals 4 times 0 squared minus 3 times 0 plus c equals 4. So that implies that c equals 4. Now we're not done here because we can write the particular velocity function, which is 4t squared minus 3t plus 4. Okay. Now we could take the velocity function and get its antiderivative to get the position function. So the position function is going to be s of t equals, now since the t was 4t squared, the new exponent is going to be 3, and we're going to multiply by the reciprocal of that, which is 1/3, but it multiplies the 4 that was already there. Similarly, with the negative 3t, the new exponent is going to be a 2, multiplied by the reciprocal of that, you would get 3 halves, plus the antiderivative of the 4 would be 4t, and then you have a plus c. Again, this is the general solution. You plug in the initial condition, s of 0, and this term is going to be 0 minus 0 plus 0 plus c equals 1. So c equals 1. Now, a lot of students end up stopping here because they got an answer, c equals 1. But the problem said to find the position and velocity functions. Well, here's the velocity function. Figure that out. Now that we know c equals 1, we can write the particular solution for velocity. So 4/3 t cubed minus 3 halves t squared plus 4t plus 1. That is the position function for this object. All right, so let's look at another example here, another motion type problem. When the brakes are applied of a car the car decelerates at a constant rate of 10 meters per second square. If the car is to stop within 2 meters after the brakes are applied, what is the maximum velocity the car could have been traveling? Express your answer in miles per hour. Okay, so um, let's the position function is going to be s of t, representing the distance in meters. Okay, so we have a couple things here. The problem's numbers and values are giving in terms of meters per second, and it wants the answer in terms of miles per hour. So we're going to have to do some conversion. Now, we know the acceleration is 10 meters per second squared, but be careful here because it says it's decelerating. So our acceleration function is negative 10. That means that the velocity function, okay, it's negative 10 because it's decelerating. The acceleration should be negative in that case. So the velocity is going to be 10t plus c. Okay. Now, when t equals 0, the velocity at 0 is going to be whatever the initial velocity is. So that's the velocity when the brakes are applied. So I'm going to use that as my constant. I don't know what it is yet, but we're going to put that in there symbolically. Okay. So then we can anti-differentiate that again to get the position function. So we add 1 to the exponent, multiply by the reciprocal, which would be times a half. So this would end up being negative 5 plus v naught times t, because v naught stands for a constant. So v naught times t would be the antiderivative in that case. And don't forget the plus c. Now, since the distance the car has traveled after is the since s is the distance the car has traveled after the brakes are applied, so at t equals 0, the initial condition would be that s of 0 equals um, 0, because the moment the brakes are applied, the car hasn't traveled anywhere because that's the moment the brakes started being applied. So if s of 0 equals 0, that means that this c value is going to equal 0. So now we have that s of t equals negative 5t squared plus v naught t. Okay. The car stops completely when the velocity equals 0. So if we set the velocity function equal to 0, then we could solve that for t and get t equals v naught over 10. So whatever v naught is, that's the amount of time it takes for the car to come to rest. So we could substitute v naught over 10 in for t in the position function. Okay, so we're going to put this in the position function. So s of v naught over 10 is negative 5 times v naught over 10 squared plus v naught times v naught over 10. Okay, so this is going to equal negative 5v naught squared over 100 plus v naught squared over 10. Now we can add these together because they're both v naught squareds. And if we did that, you would end up with v naught squared over 20. Okay? So if the car is to stop within 20 meters, then s has to be less than or equal to 20. So v naught squared over 20 has to be less than or equal to 20. Or if we solve that for v naught squared, that has to be less than or equal to 400. So if you take the square root, then v naught equals 20 meters per second. So to express 20 meters per second in miles per hour. We just need to do the conversion. So 20 meters per second times 1 kilometer for 1,000 meters. So I'm just converting the number into kilometers per second. And then we're going to change that out seconds into hours. So 3,600 seconds over 1 hour. All right, so that's going to give us 72 kilometers per hour. And then I can multiply that by the conversion for miles to kilometers. Each mile is 1.6 kilometers, so it's 1 mile over 1.6 kilometers. The units cancel there, and you get 45 miles per hour. Okay, so that's what we would have for the answer for that one. So that's the car's maximum velocity to stop within 20 meters is it would have to be going no faster than 45 miles per hour. All right, guys. Hope that was helpful to you. Take care.